Thanks for the invitation to talk here. Hopefully, the talk here will deliver on exactly what it says in the tin in terms of talking about line intensity mapping and how it will hopefully let us pursue multiple lines of inquiry through various spectral lines into the epochs that we call cosmic dawn and cosmic noon. And just to give a really brief, broad overview of what I want to talk about, I want to talk about what's out there and how we currently survey what's out there in terms of the various processes of star formation and galaxy formation from the Big Bang up to the present day. I want to talk briefly about where conventional surveys might be limited and how line intensity mapping might complement those conventional galaxy surveys. And then in the last quarter or so of the talk, I do want to just give a brief overview of a couple of the experiments mentioned that I am involved in and the general status of the experimental landscape for line intensity mapping surveys. But as we're only going to start to shed light on the topics during this talk, I think it's appropriate that we start for now in darkness, or at least apparent darkness. If you are lucky enough to have access to a location without too much light pollution, you can look up at the sky and you can see all the stars. Maybe you're lucky enough to see, the clouds of the Milky Way, or even the Andromeda Galaxy if you're really lucky. But by and large, the night sky is not completely bright because our universe is not static and because it has a finite observable extent. There are parts of the sky that at least appear to be completely blank. And when the Hubble Space Telescope launched in the mid-90s, and once they fixed the optics so it delivered on the resolution that was originally promised, astronomers realized they could study very distant, faint galaxies that might be hiding in this apparent darkness with unprecedented sensitivity and resolution. And so they wanted to pick an image, they wanted to pick an undistinguished typical patch of blank sky to image over dozens of hours of observing time. Now, there are actually good reasons to image portions of the sky that appear to have nothing in it. If you're aiming to resolve these very distant and therefore at least extrinsically faint galaxies, you want to eliminate stray light from sources in your foreground. Especially, you have to be cautious if you want to encourage follow-up at other wavelengths. It's no good if your field is completely quiet and visible or infrared wavelengths, but then has a great big radio loud quasar sitting in the middle of it, overpowering any faint sources that you want to survey in the radio or even in the far infrared. So that's a pretty good practical reason to try and target blank sky. The other nice consequence of that is that the statistics of any object counts, if you're trying to figure out how many galaxies you would expect in the observable universe, should be unbiased. It may be subject to a lot of variance if you're surveying a very small field of sky very deeply. But variance aside, there should be no a priori bias to your results. Now, this takes many hundreds, many orbits, hundreds of hours. And that's a lot of time for an instrument like Hubble, where the whole community of astronomers is competing for observing time. But fortunately, in this particular case, one of the astronomers interested happened to be the director of the Space Telescope Science Institute, and director's discretionary time is a thing. Not to say that the director did that all by the director herself. Obviously, there was a group, there were committees formed, there was proper survey design going on, and they selected this patch of sky around the constellation of Ursa Major. Now, the previous slide is a completely black slide. I have to say that's a little misleading because even with a wide optical image from the digital sky survey here, it's not a completely dark patch of sky. You can zoom in and you can see, maybe you can see the few really faint foreground stars that are very, very faintly resolved in this kind of low resolution image. Unfortunately, this is the best I could find at kind of short notice. But, by and large, there's no great big booming star visible in the field like this, like some of the stars you can see outside of the field in this wider field image. So as they selected this patch, they managed to get around something in the neighborhood of around 100 hours on Hubble. And when they imaged it, this is what they found. It's full of stars. Well, you can't really resolve a lot of the individual stars, but certainly you can see it's full of galaxies. And not only that, galaxies often from very, very early cosmic epochs. This was unprecedented at the time. The sensitivity and resolution of Hubble was unique, potentially is even unique to a certain extent today, at least for optical or near-infrared observations. Space gives you a significant advantage in that the atmosphere scatters a lot of your space light and limits the seeing, limits the resolution to achieve, but not so for Hubble. And so this was a really paradigm-shifting moment where these deep observations were revealing galaxies often from the first billion years or so out of around 13.5 to 14 total observable cosmic history. And these galaxies are very regularly shaped. They are all kinds of different colors. So you have this very diverse, very heterogeneous population of early galaxies looking very different from the galaxies that we'd recognize today in our local group or in our sort of local universe at redshift 0 or 0.01, 0.1-ish. Now, one of the key things about patches like this, apart from the impressive nature of Hubble imagery by itself, is the potential to observe in other wavelengths so that we can get a more complete picture of these galaxies, including through ground-based observations. If you want, the Hubble operates at visible to near-infrared wavelengths. If you want to observe at longer wavelengths at similar angular resolution, that requires much larger telescopes, and they're easier to build on the ground, where longer wavelength light is also less scattered by the atmosphere. Now, this patch, the Hubble Deep Field, or the Northern Hubble Deep Field, is not the only patch that Hubble would end up observing in this way. There was a companion field in the southern sky, as well as the Hubble Ultra Deep Field. And this was recently targeted by a very sophisticated millimeter wave telescope. So on the left, you have Hubble, which we recognize. It's sort of our great observatory, our visible to near-infrared wavelength light bucket in Earth orbit. On the ground, on the right-hand side, what I'm showing is the Atacama Large Millimeter stroke Submillimeter Array. This is in the Atacama Desert in Chile. It is dozens of antennae working together as an interferometer. What is probably the world's most sophisticated millimeter wave interferometer in operation today. And through observations of the Hubble Ultra Deep Field, with this instrument on the right-hand side, you can actually get a different view of the kinds of galaxies that live in that field. So on the left-hand side is an image similar to what I just showed you before, except in the ultra deep field instead of the older deep field. And you can see the starlight from these galaxies, often, again, in the first billion years or so of the universe. And then on the right-hand side, ALMA millimeter wave observations, you can see are very successful at measuring some of this emission, which is coming from the dust and gas content of these distant galaxies. Now, I do want to step back and talk about why galaxies from the first billion years or so are interesting to us as astronomers, as astrophysicists, as cosmologists. So I want to take a step back from this picture, which is small in the scale of things because it's looking at several square arc minutes. And I want to step back into the really big picture, which is to say the entire observable history of the universe. Now, I'm not going to give a full lecture on physical cosmology right now. That would take an entire semester. However, what I would like to note, at least briefly, is that around the present-day universe on the right-hand side and around the primordial universe on the left-hand side, we now have somewhere between half a century and a full century's worth of observational cosmology behind each of those. So with the primordial firewall back there, surveys of the cosmic microwave background and the fluctuations in the microwave background more specifically have served as very strong validation of the standard model of cosmology. While closer to home, we have galaxy redshift surveys that have been getting larger and larger in scope and better at constraining cosmic expansion and the evolution of large-scale structure around the present day on their own, as well as in conjunction with other probes like CMB surveys. But I think in comparison to the amount of knowledge we've built up on each of those ends, we're really only starting to get direct insight into the middle bit of cosmic history in comparatively more recent times. And to be fair, there is a lot going on, and I want to talk a little bit about what's going on, which is basically cosmic dawn through cosmic noon in more colloquial terms. So one of the more interesting bits of cosmic history is what we call the epoch of reionization. This is cosmic dawn. Now, for a good several 100 million years following the Big Bang and following the emission of the CMB, we have what's called the dark ages, because the universe has cooled down from being this highly energetic fluid of baryons and photons, baryons in particular being an ionized state, to basically the photons free streaming on their own, being the cosmic background background, and then the baryon matter, which is cooled down and combined into neutral hydrogen. And really nothing much more exciting. Neutral hydrogen doesn't really emit much. It's pretty opaque. And so that's why we term it the dark ages. But at some point, once things start gravitationally collapsing, you can work your way along the picture from the left-hand side to the right-hand side, because the first stars, well, really proto-stars, start forming, and they start assembling into these proto-galaxies. They emit ionizing radiation, and that reionizes, because the primordial universe had ionized baryonic matter, reionizes the surrounding medium. And you start to have these ionized bubbles growing and growing until they start overlapping on top of each other. And ultimately, the intergalactic medium becomes mostly ionized, with maybe some pockets of neutral matter remaining. And all of this process of reionization happens within the first billion years after the Big Bang. And over the next 12 gigayears, the next 12 billion years, we see galaxies continue to evolve, becoming the kinds of galaxies we recognize today. Star formation continues to ramp up until we end up with basically kind of the universe we know. Now, galaxies from the first billion years or so are much more difficult to observe than galaxies at redshift 1 or so, from the last few billion years. The galaxies from the first billion years are much further away, so they're extrinsically faint already, and they're also intrinsically faint. Remember, these are proto-galaxies. They're very different from the galaxies we recognize today. And of course, there have been these deep surveys that I talked about in the Hubble Deep Field and Hubble Ultra Deep Field and so forth, that have identified a selection of objects. And there will be further deep surveys with future instruments like the James Webb Space Telescope or the Nancy Grace Roman Space Telescope that are going to delve deeper and in longer wavelengths as well to provide views distinct from what Hubble can provide. But there's still lots of interesting open questions here. For example, reionization. Well, how much faint galaxies contribute to reionization versus bright galaxies is not a completely settled question. Is it that there are lots of fainter galaxies that ionize the medium, or is it a smaller population of very bright galaxies that dominate the process? Cosmic star formation activity has a history that's not completely understood yet in terms of when it peaks, when we reach cosmic noon, so to speak, and when it begins to decline. We know that it declines in the last billion years or so of cosmic history, but we're not quite sure when it peaks and when it kind of drops off. To answer these kinds of questions on a really cosmic scale, we possibly want a wider survey than something like Hubble has managed with the deep fields, even though they're very impressive, and things like James Webb will manage at similar scales. Just to give a sense of perspective, this is a useful plot from a paper that's referenced here. This is, I believe, a simulation of large-scale structure, the cosmic web, so to speak, at redshift 2, with some field sizes overlaid. Various fields, including the Hubble Deep Field North, you can see HDFN, as well as the Hubble Ultra Deep Field, HUDF. You can see that these very small square arc minute scale fields don't even really begin to span an appreciable extent of the cosmic web, at least along the transverse dimensions, along the angular dimensions. So in order to statistically gauge the contributions of all galaxies, bright and faint, on a cosmically meaningful scale to processes like reionization and cosmic star formation history, you potentially want to go a bit wider while still trying to get a handle on these fainter populations of galaxies. So I know I went through a lot of information on this in this first 15 minutes or so. So I want to pause a little bit and recap what I think are sort of the key points so far. There's no denying that astronomical instrumentation has reached a really impressive point, both from space and on the ground. And they allow us to sample faint, very distant galaxies in many shades, optical, infrared, millimeter wave, so forth. And in particular, conventional imaging surveys have been quite successful in two extremes. One extreme is measuring large-scale structure traced by present-day galaxies. The other extreme is surveying individual faint distant galaxies in very small fields. But trying to survey faint distant galaxies over larger fields so far seems to be quite challenging with conventional imaging, where you're trying to resolve individual galaxies and their redshifts. Surveys tracing fluctuations in a kind of background radiation, for example, the cosmic microwave background, have been quite successful in characterizing the early universe. In addition to the microwave background, there is also a cosmic infrared background, which I'll come back to in a little bit, which is coming from closer to home, maybe redshift 1 to 2, so still rather ancient, but not primordial. Both the cosmic microwave background observations and the cosmic infrared background observations leverage the statistics of fluctuations in the background across large cosmic volumes in order to characterize the early universe. But they are broadband observations. They are designed to be broadband observations, and they're designed to provide only a two-dimensional picture. So they don't really give us a three-dimensional picture of the large-scale structure at early times, not that they are supposed to. So with all of these points in mind, you may be able to see where line intensity mapping comes in. So in the broadest sense, in a more formal way to define things, line intensity mapping is a technique where we undertake a blind statistical survey of emission from a given spectral line from a population of galaxies spanning a certain kind of defined survey volume. The informal way I might describe it is we're trying to survey galaxies without actually surveying galaxies. We're only trying to capture the aggregate line emission from both faint and bright galaxies. Because here's the figure of a sort of hypothetical high redshift galaxy spectrum from microwave to radio, and you can see there are all these different spectral lines, and these spectral lines will be present in the spectra of both faint and bright galaxies, just at different luminosities. The fact that these lines are emitting at these very specific frequencies is important, because specific frequencies, specific observing frequencies, are associated with specific redshifts, and so specific points along the line of sight because of the expansion of the universe. As a point of contrast, if you wanted to try and map the intensity of the overall emissions shown in this diagram, in this flux spectrum, in the rest frame infrared continuum, you could try that. And this is what we would do if we were to measure the cosmic infrared background. That's coming from the whole population of redshift 1 to 2-ish galaxies dominantly. But the thing with that is, again, because you're undertaking a broadband measurement of the total brightness across this spectral range, you're going to have a difficult time disentangling bright distant galaxies from faint nearby galaxies if you're trying to analyze the CIB. So with line intensity mapping, we're going to try to take a three-dimensional data cube across the sky and in frequency space. And that will give us an idea of how fluctuations in integrated line intensity and the associated processes like star formation evolve across cosmic time. Again, we're talking about these, spectral lines associated with various atomic or molecular species. I'm not going to go into too much detail. I just want to show you that there's just a wide variety of transitions in these atoms and molecules, and spectral line emission can come from a variety of different mechanisms. You may have heard of 21 centimeter emission. This is a hyperfine transition in neutral atomic hydrogen. Now, this hyperfine transition intrinsically is very rare, but there's a lot of hydrogen in the universe. It's our most abundant element. And so 21 centimeter emission in particular is basically sure to exist even in the dark ages. It's just a matter of how bright it is and how detectable it is relative to various observational foregrounds, as well as instrument sensitivity. Then we have molecules like carbon monoxide on the lower left there, which has an electric dipole moment, unlike molecular hydrogen, which is symmetric. And so the fact that that electric dipole moment exists means there's a coupling to the electromagnetic field. So transitions in rotational energy states result in a whole ladder of lines. For each of these, allow transitions by one step in rotational energy. And then on the right-hand side, I'm just illustrating the atomic line from ionized carbon, C2 line, which comes from fine structure transition. So just a wide variety of lines. And it's all well and good physically to try and understand the physical mechanisms, but for this talk, I really want to focus more on astrophysically, qualitatively, where these lines come from in a given galaxy. So let's look at the Large Magellanic Cloud, which is one of the Milky Way satellite galaxies. So on the left is Hubble imagery, very impressive, very nice. Nice clear picture of the stars and the Large Magellanic Cloud. On the right-hand side is a map in 21 centimeter emission. Now, this emission is coming from the neutral hydrogen. So as you might imagine, it's mostly coming from the diffuse medium surrounding the galaxy, and the qualitative nature of the picture demonstrates this. Meanwhile, there is another hydrogen line, H alpha. That's tracing ionized hydrogen, hydrogen that was neutral, but then is ionized by the light from newly forming stars. And you can see that that seems to be mirrored quite well in the optical image, because H alpha is a rest frame optical line. Then you have the CO lines that I talked about, CO1 to 0 in particular. Here is an image of the LMC in CO1 to 0. And that is tracing cold molecular gas, which is the fuel for star formation activity, at least in regions where there is enough dust to shield the CO gas from surrounding ionizing radiation or to energize it excessively. And of course, if we put this CO data together with the other data sets that I showed you, the 21 centimeter map, as well as the H alpha map, that's when you have a really full idea of where the stars are forming in this galaxy, where the molecular clouds are, where things are just kind of undisturbed, diffuse, neutral hydrogen. And all of this is what lets us figure out the overall state of the interstellar medium of the ISM in this galaxy. Now, I have mentioned C2, so I will show you a C2 map. It's not as pretty. It's a relatively low resolution map, but it does show you that what the C2 traces in the LMC, at least, is actually quite similar to what the H alpha traces, at least again in this system. Now, H alpha is rest frame visible, and C2 is rest frame far infrared. Now, that's important because in dusty star forming regions, you will find a lot of shorter wavelength radiation, like H alpha emission, gets absorbed by dust, is reprocessed, and then it's re-emitted in the infrared, including in the C2 line. And so C2 is potentially a better line to target than something like H alpha if you expect your galaxy to be very dusty or otherwise high metallicity enough, in jargonic terms, for ionized carbon to be at least reasonably abundant. And of course, I'm just illustrating these lines in a single system, in a single galaxy. But the key thing about line intensity mapping is for the science goals that it targets, which is getting a statistical handle on cosmic processes at large scales, we don't really care about resolving or confusing individual emitters. What we want to trace is the clustering signature of fluctuations in the integrated line intensity, aggregated across all emitters on larger scales. So it's maybe useful to provide a visual contrast of this idea with a more conventional approach to measuring CO with large community instrument. Similar to ALMA, here we'll be using an example of the Very Large Array, which is a similar interferometer in New Mexico, just operating at longer wavelengths. Now, this is simulation, of course, but the broader point is that the VLA is a very good instrument for targeted surveys or very deep surveys. But if you wanted to carry out an untargeted search across a few square degrees even, then you could spend several thousand hours on a VLA-like instrument, and it would still only get you the tip of the iceberg because of your field of view, the sensitivity, and the requirements, and so forth. Now consider the picture on the right. We're looking at the same slice of space in this simulation, but because each of those gray dots on the left-hand side is a CO emitter, each of those gray dots has a spectrum with a CO1 to 0 line in it. And the aggregated flux from the emission from that CO1 to 0 line is going to trace the large-scale structure of the galaxies, of the underlying dark matter in this field. And you don't need to identify individual emitters. Here we're looking at the CO flux through a 5 arc-minute beam. That's a fairly large beam in the scheme of things. But if you can map this out with the 5 arc-minute beam, well, you don't need a highly sophisticated interferometer like the VLA to map out the large-scale clustering. You just need a single 10-meter dish, which is a big difference. And again, looking at the flux rather than searching for sources, you're not only getting fluctuations in the CO flux due to brighter emitters, you're also getting structures and filaments in the flux fluctuations from the fainter emitters taken together, as long as you spend enough time on the field to integrate deep enough. Now, that might sound a little facetious, just saying integrate deep enough, but it's easier to pull off with a small to mid-scale dedicated instrument that's just a single dish with a decent receiver, compared to a big community instrument like ALMA or the VLA, which has to juggle lots of different priorities. Even director's discretionary time has its limits, even if you are the director of a facility like that. And of course, just to remind you, this is a two-dimensional visualization, but unlike the cosmic background measurements I talked about, this is a three-dimensional measurement. You're going to get line of sight information. You're going to get basically an angular map like this across multiple frequency channels spanning your observed band. Now, as I emphasized, different lines, different spectral lines probe different phenomena in the ISM and different regions and galaxies in the ISM. And so they're going to provide different views into the same key cosmic processes. So it's important actually for all these different experiments, particularly the 21 centimeter line, to be looking towards the first billion years. And for multiple projects, to be targeting each of these lines in multiple lines of inquiry, because each project is going to have its own design, it's going to have its own instrumental design, it's going to have its own survey design, it's going to be looking at different spatial scales from other instruments, it's going to be looking at different redshifts from other surveys, and so on. Now, the experiments that I work on are not so much in the 21 centimeter scheme of things, although Toronto, of course, has significant involvement with experiments like Chung and even the square kilometer array. My personal involvement in looking at simulation of these kinds of signals is mostly on the COC2 wheelhouse of things. And so we're at sort of the last quarter of the talk, and I want to spend the remaining time just talking about some of these experiments in slightly more detail, and talk about the general status of these experiments as well. So in terms of, this small to mid-scale dedicated instrument, all of these are these kinds of small to mid-scale dedicated instruments. And COMAP in particular is trying to be that for single dish line intensity mapping of CO lines. Now, as I mentioned, CO is tracing the cold molecular gas that fuels star formation. So it's not too surprising that it would correlate very well with star formation rate. which it does across a range of low and high redshift galaxies, shown on the right-hand side here with the sort of broadband far infrared luminosity acting as a proxy for star formation rate on the y-axis versus the CO line luminosity on the x-axis. It's the most common molecular species that emits appreciably brightly in this kind of line. And so that's why we hope to ultimately be using the CO ladder lines to probe the epoch of ionization with COMAP, which is the CO mapping array project. Now we think CO will be a useful probe on its own, tracing the formation of the emitters ionizing the universe, but then of course, it's going to be even better if you're using that in conjunction with other series, such as in 21 centimeter, where you're tracing the neutral IGM, the neutral intergalactic medium that's being ionized. Now, even if CO is supposed to be a nice bright line, it turns out we probably need pretty substantial investment to go after CO from the epoch of ionization at an acceptable level of sensitivity, even trying to carry out unresolved line intensity mapping rather than a conventional resolved galaxy survey. So currently, COMAP is in a Pathfinder phase to build sort of groundwork for that kind of ultimately ambitious experiment. And this is where having a whole ladder of CO transitions comes in, because the Pathfinder is observing in a band centered around 30 gigahertz. And that actually corresponds to a couple of different CO lines. So you have a epoch of ionization signal in principle in CO2 to 1 coming from redshift 7 or so from cosmic dawn. But what's going to dominate our observations in the Pathfinder phase is a much brighter signal coming from lower redshift at redshift 3 or so in the CO1 to 0 line. That's still at least 10 billion years ago, but it's going to be a much brighter signal, not just because it's closer to us than the reionization epoch. It's very near the peak of cosmic star formation activity that I talked about in this epoch of modern galaxy assembly, or the cosmic noon, so to speak. And so for one, observing in this sort of 30 gigahertz band, spectroscopically, of course, so you get a three-dimensional picture, that lets us access this signal from redshift 3, marked out in red there. And that's interesting in its own right. But then as a bonus, of course, this observation still has fluctuations in the higher redshift CO2 to 1 buried in it somewhere. And that's something we can potentially extract or set limits on through further observations as the project sort of progresses beyond its Pathfinder phase, or maybe even a more advanced analyses potentially in conjunction with external data sets. So this is the COMAP collaboration. As you can see, it's a very broad range of institutions across North America and Europe. The actual instrument is on a Caltech-owned site, the Owens Valley Radio Observatory, which is pictured on the right there. It's Central or South California, depending on what you define as Central California and what you define as Southern California. I think it's probably closer to Central California. It's in the Owens Valley, nestled in the middle of the Sierras. And so, all of these different institutions and people at these institutions are working on all kinds of different aspects. Toronto, CETA has been very much involved in modeling the signal, in particular, working with collaborators at York University, Geneva, and so forth, as well as Oslo. Here's the instrument from a little bit closer up. So on the lower left, you can see it before it's been fully assembled. You can see that there are 19 feeds, which doesn't sound like a massive focal plane compared to the thousands of pixels you'd be operating with at shorter wavelengths, and of course the millions of pixels you operate with in visible wavelengths. However, it still takes a lot to support, as you can see on the right-hand side there. That's the real back end that converts the output of those feed horns into spectra. So this is operating. It's mounted on telescope, as you can see on the upper left there, shielded from the elements with that massive shroud. It has been operating since about 2 summers ago, and we're actually prepping early science results, trying to get them to come out this year, but we'll see. So I think COMAP is a very promising instrument And the survey is going to have pretty strong science that could come out of it, especially with cross correlations with the other surveys that operate at similar redshifts. But I do think, in addition to CO intensity mapping with things like COMAP, there is a really compelling case for intensity mapping with the C2 line. So I want to talk about that in the last few minutes I have. Now, C2, like CO, is a pretty bright line. In fact, looking at the broadband IR luminosity of certain star-forming galaxies, the C2 luminosity alone can make up around 1% of that, which is a lot when you consider that it's just a single species. It's just this single atomic spectral line on top of this massive, gray body continuum emission density spectrum. As I said before, C2 is tracing the ionized interstellar medium. And it traces it in a way that's not as attenuated by dust as something like H alpha. Now, maybe saying that C2 is a star formation rate indicator is a bit strong, but certainly we think it's an excellent signpost for star formation activity because a substantial amount of C2 emission is correlated with star formation in the way I described. We certainly think it's an excellent signpost locally, and we hope that that applies at high redshifts as well. And by now I hope it's really clear that in probing reionization, 21 centimeters CO and C2, this triplet is a strongly complementary set of radio and far infrared lines because 21 centimeters is probing the neutral medium, and so it's probing the topology of these ionized bubbles directly, and CO and C2 are tracing the star formation activity, the emitters that drive the reionization process. Now with CO, there's an additional caveat, which is that the molecular gas, to be CO bright, needs to be shielded in dusty regions. And if the proto-galaxies at cosmic dawn are not that dusty, well, the CO is going to end up photodissociating because of these ionizing photons. And that's going to form regions of ionized carbon that emits in C2. So because of that, C2 is going to have an additional dimension of interest as a star formation tracer here at the epoch of reionization. So these are the kind of experiments. I really don't have a lot of time left. So here, I'm just going to give a really brief overview. TIME is the tomographical ionized carbon mapping experiment. Trust me, that experiment makes sense. The PI is Professor Abby Kreitz, who was at Toronto until recently. She's now at Cornell. Concerto is an experiment led by the French at Marseille. It is actually being deployed in Chile right now at one of the telescopes in the Atacama Desert. There's also CCAT Prime, which has substantial involvement from the University of Toronto. The telescope is under construction. It's expected to see first light by 2023. And there's a lot of jargon on the slides here, I apologize. But suffice it to say that all of the experiments have a common target, which is C2 emission from the epoch reionization. But they have very different designs. They have different approaches to instrumentation, as well as different approaches to survey design. And so it's very exciting to think that all of these different approaches will be happening and making detections, or at least setting down limits as we go through this next decade. And so, that's where things stand with the C2 experiments. And I think it's a very exciting time to be involved in these, where these experiments are getting built up and are going to start observing sometime in the next few years. So I really don't have any time left. I am just going to summarize briefly what I think the really interesting points are. And the key thing is that line intensity mapping as a whole, as this technique, is going to hopefully fill a niche between the wider spectroscopic surveys like the Sloan Digital Sky Survey or DESI that you may have heard of, and the deeper spectroscopic surveys, or even the deeper photometric surveys like the Hubble Ultra Deep Field surveys and so forth. And it's going to do that by surveying line emission in an aggregate from both faint and bright sources over large cosmological volumes. And I talked to you a little bit more in detail about a couple of experiments, including the COMAP Pathfinder, which is this experiment that's going to map fluctuations in CO emission at redshift 3 in the Pathfinder phase and try to constrain molecular gas content at cosmic noon, with future phases trying to aim for reionization. And I want to end off again by saying line intensity mapping across these multiple lines, 21 centimeters, CO and C2, all together. That's really what's going to provide a really powerful probe of cosmic dawn, what's going on with the topology of the ionized bubbles, as well as diagnostics of the interstellar medium in the way that I illustrated you with the single system of the LMC. So that's, I think, all the time I'm going to give myself, and I'm going to open myself up to questions. Thank you very much.
Thank you very much. It was very exciting to learn. Feel free to add any questions in the chat if anyone has any from the audience. I have a question from myself. How do you think that the James Webb Space Telescope introduction will affect research with line intensity mapping?
Well, I think it's going to be a great opportunity because what things like James Webb and Nancy Grace Roman will allow us to do in the future is get pictures of individual objects from cosmic dawn, from cosmic noon. And that's still important because we have said CO is an indicator of star formation activity. C2 is an excellent signpost for star formation activity. But the conversion from aggregate CO intensity to physical quantities like star formation rate, like even molecular gas mass, we currently only really have local calibrations of those. So it's going to be important to continue to observe with things like James Webb and Nancy Grace Roman in order to get a more complete picture of individual galaxies, individual early type galaxies, so that we can calibrate our expectations for how to convert not raw, but somewhat processed line intensity mapping results where we get an idea of the fluctuations of CO and C2 and convert that into physical results like cosmic star formation history, molecular gas history, and so forth. So I think that will be a great benefit to the line intensity mapping community, as well as obviously the astronomical community at large.
Awesome.
I have a question. I'm not really in like astronomy or astrophysics. So I don't really know what Z squiggly line like 3 or 7 means.
Oh, so I just mean to say redshift of 3 or so, redshift of 7 or so. So in really quickly speaking, as I said, light is redshifted by the expansion of space, and the amount by which light is redshifted depends on how distant the origin of that light is. Because the expansion of space is stretching out the wavelength of light,
right?
You can say, well, okay, so if the rest frame wavelength is a centimeter, if light is coming from a distance sufficient that 1 centimeter wavelength is stretched out to 2 centimeters, that's a scale factor of a half, which is to say a redshift of 1, because it's invert the scale factor, subtract 1. So redshift of 3, the wavelength has been stretched out by a factor of 4. Redshift of 7, the wavelength has been stretched out by a factor of 8. The conversion between redshift and actual sort of cosmic time, look back time, is mathematically involved. There are various differential equations you have to integrate. in order to go from redshift to look-back time by accounting for the expansion history of the universe and the different components that influence that expansion history. But redshift is kind of the sort of heuristic we use typically to often describe observations of early universe things, because the look-back time also is going to depend on your cosmological assumptions, whereas redshift is redshift. If light's been redshifted, if the wavelength is stretched out by a factor of 4, it's been stretched out by a factor of 4, regardless of how distant you think it is.
Oh, so it's like a measure of distance. It's like a universal measure of distance.
Yeah, it's kind of it's a model independent measure of basically how far back we think we're looking. Yes.
Oh, okay. Thank you.
I had a general question about like a bit less on the research directly, but about the management of the research. How does it work to, in your experience, to collaborate with astronomers and researchers from all these different institutions? Because on the earlier slide, there really is like a large number, in my view, of people from different countries and institutions.
Yeah, I mean, in the grand scheme of things, funnily enough, this is not a large collaboration. You look at something like the future CMB experiments. That's hundreds of people across dozens of institutions, if not approaching around 100. This is a relatively small thing, and I do think it is interesting to still be working in a relatively close-knit collaboration in a time where we are kind of trying to leverage larger collaborations, larger sort of community instruments, oftentimes in the service of early universe studies. There are obviously a lot of practical aspects to negotiate when you collaborate, collaborators across the ocean, across the pond. The trivial things like data transfer becomes interesting. And obviously, pre-COVID, there was a non-negligible amount of travel across the pond as well. However, I think a lot of times it's not too bad. Especially in the modern day, where everyone can sort of collaborate over the internet. It's certainly better than trying to. It's certainly better than trying to. I don't know. No, I think people still do mail hard disks across oceans in certain contexts. But yeah, I think it's an interesting experience. You'll have to ask me that question again if I ever get involved in a actual large collaboration involving lots of institutions. In this kind of context, I do think this is still kind of a collaboration size where everyone has a definite role that doesn't overlap too much with anyone else's role. I think for example, you can have just a handful of people working on signal forecasting, and each of those people have a specific niche within that. Whereas I think with the large collaborations, you start to have multiple people working together on the same topic.